Hello everyone. For this lab we are going to work on the diesel engine cycle. This is one to remember. The analysis concepts explained here are maybe very helpful during your professional career while working on diesel engines. And at the end of this lab, you should be able to get familiarized with the thermodynamics of work and efficiency in a modern turbocharged diesel engine. And you will probably be surprised to see that the large amount of practical engine information that you can get, operation information you can obtain through this analysis and the analysis of data, which are relatively simple to obtain in the engine room. Well, as a quick background regarding where the data that we will use during the lab come from, Professor Sarnacki and Wallace were at the origin of the medium speed engine lab, or otherwise called MSEL. The objective was to provide an independent, unbiased research lab for MMA, but also for external clients, research, in particular on fuel testing. MMA has played a significant role in the R&D effort of large companies, so it has been successful. Additionally, the MSEL itself, the Medium Speed Engine Lab, is a fully instrumented engine room simulator. So here you can see a picture of the engine and the engine room, and that engine is, as you can see on the pictures, it is set up like an engine room. The engine includes all auxiliary systems required to make the engine run. So, like you have here a fuel skid with some modifications, FO purification, lube oil purification, and freshwater closed loop, with seawater open loop cooling. So that is the background. Now, if we go to let's talk about the diesel cycle, which is also known as the constant pressure heat addition cycle. As you know, a cycle is a closed loop by definition, and so let me go over that. If I can change my page. Seem to have difficulties here with this. Here we go. So here is the cycle. So we have 4 points. You see 1, 2, 3, 4. So basically what is happening during this cycle is that here you got some fresh air admitted in the cylinders, and you have a compression. You compress the air and you get to 2. That process is a diabatic compression. Diabatic meaning there is no heat transfer, and that is represented here in state 1. You see you have air. That is maximum volume in the cylinder, full of air, and then you compress it, you go to 2, and state 2 is here. It's just as the air is compressed fully, so the volume is minimum here, and 2 minimum. And then this is when you you send, this is when the combustion happens. So you put heat in, and that's a fuel injection, actually, moment. And as you see, this is PV. That's I should maybe have started by that. That's a PV diagram, pressure volume diagram, which is always used for describing cycles like the diesel cycle or the Otto cycle, the one for gas and gasoline engines. But this one is a diesel cycle again. And so, well, back on what we were saying, here is the combustion. You see it's happening at constant pressure, which is isobaric heating. Isobaric means constant pressure. And then state 3, this is the expansion of gas. So after the fuel injections happen, the fuel is burning, causing an expansion. And this expansion is considered also adiabatic, which is no heat transfer. And so it's following this line. And then you arrive at the point where your volume again is maximum. So the cylinder is completely, the gases are completely expanded. And we start all over again to state 1. We admit fresh air, and then we start compressing again. Fuel injection here, so we put some heat in, etc., etc. So one important thing is that the area here is under that curve is actually the work here. So it is the integral of the pressure as a function of the volume, as you can see. And that's and I will describe what it is a little bit later. I will get there, but it's not that difficult, you will see. Here are some, here is the expression of the maximum theoretical efficiency of a diesel engine. So it's a maximum efficiency. It's so there is some terminology, some vocabulary to remember here. You can see eta theoretical is this expression, again, maximum theoretical efficiency, where R is the compression ratio. Typically it's it's 15 to 1, between 15 to 1 and 23 to 1 for a diesel engine. Here you got another factor, which is called the heat capacity ratio. Just know it's 1.4 for ideal gas, so it's a value we are going to use, 1.4. And here the cutoff ratio, alpha, which is this term here, is actually nothing less than the ratio for V2, which is the volume of air before combustion, and V3, which is volume of air after combustion, the volume after combustion. So V3 over V2. Again, this is just to remember, because this is going to be helpful for the rest of what we are going to do. Now, we spoke about the theoretical diesel cycle. Here is the real diesel cycle, which is much more banana shaped than the previous one even. It is still a PV diagram, as you see, pressure, volume. And why is there a difference between the theoretical and the real? It is because in reality the combustion is not at constant pressure as we said it was. You see, constant pressure here, but it's not really like that. And there are other factors like incomplete combustion, losses, etc. that makes this cycle finally look like that. But the ideal cycle is not too much far off. It serves as a good basis for calculation as well, or comparison. So, and you can see the work is still and always the integral of B dV. So how do we develop a real PV diagram? The pressure here can be measured. You know, they are devices, pressure devices. You can record, graph the pressure directly connecting them on the cylinders of on the engine cylinders, one by one, and then you get a reading of the pressure. But now the volume cannot be measured directly on an engine. It cannot, only the pressure. So how do we create this real diesel cycle? What we do is take the crank angle versus the cylinder pressure here. So say we can measure the pressure and the crank angle. We get it easily. It's a signal that comes from an encoder on the crankshaft. So it's pretty easy. So you see how the profile of this, the profile of the pressure is as the crank rotates. You can see here the intake is very low pressure here, and then it's when the compression starts, and it goes up, and it gets to this point where you start injecting the fuel, and then there's an expansion. So that is, the pressure gets down really, really quickly, and then there is the exhaust where the pressure is minimum as well, and it keeps on doing this over and over and over. It's a cycle again. So you would wonder what the TDC is. It's the top dead center. So how do we turn that into traditionally how can it be turned into a pressure versus crank angle? Can we turn that into a PV diagram? Well, generally what is being done, what was done is you fold the page here that you have, you print that, you fold it in half, and you use the TDC line here as your folding point. And then looking through the sheet, you will see it makes that banana shape a real diesel cycle. But with Excel, now we and computers where we can acquire signals quite easily. With Excel, we need all the data. So what is being done, what we use is a fairly complex equation, but with a computer and Excel, it doesn't really matter if it's complex. Once it's entered, all the calculation is pretty straightforward, easy to do. Just cut and paste and transport from one cell to another. You know that. So this is the yeah, again, fairly complicated formula that will be entered in the Excel spreadsheet. And here, you know, that's a volume. And that basically the idea behind that equation is that it connects the volume that we want, you know, from that integral, if I can find it again. Yeah, it connects the volume and the cylinder volume. The cylinder volume is Vd here that you can see. It's just calculating the volume of the cylinder here, the displacement basically, the displaced volume, and it's V, the volume of the cylinder is, which is here, V sub D is pi over 4 times the bore being the diameter, inner diameter of the cylinder, bore squared times the stroke. The stroke is that the displacement, the net displacement of the piston. So this math here comes from the calculation of the position of the piston and with respect to the crank angle. Basically, it's about drawing a crank circle and resolve for the piston pin from crank center, piston pin distance for crank center, and crank angle theta. So here are the parameters we just spoke about. Vd, the volume here, about the bore, the stroke, the connecting rod length L here, compression ratio R, and here is theta, which is the crank angle. Now, how do we get the work? We saw that the work is the area under the curve. That it is the integral of the pressure as a function of volume. Well, basically what we do, and it's a pretty practical and simple approach, instead of to calculate the integral, we take an approximation, which is chopping the area under the curve into multiple trapezoid. Here is one. And each one of these trapezoid is has a width of a fraction of the volume V. So you see we take a little slice of that volume V here, and the work under that line here for that trapezoid is this surface. And now we just have to calculate the area of the trapezoid, and it's pretty straightforward. There is a rule for that called the Trapezoidal Rule, and it's widely used for approximating the definite integral. It's a very practical way of resolving that sort of problem. And recall the area of the trapezoid. Here it is. Here's our curve. Here you've got the height of the trapezoid. Here you have the first base B1 and the second base B2. And what we want to calculate is the area of that trapezoid. So here it is, that this equation, it's the height, sorry about that, it's the height of the trapezoid multiplied by the sum of the bases B1 and B2 divided by 2. As simple as that. Now we are going to apply that rule to the whole curve, and like this. So you see we keep on chopping the area under the curve this way, so it makes multiple areas, and each one of these areas here represent the work done during each infinitesimal step, and the sum again of all these areas starting here at this volume and ending at the max volume. Eventually, after calculating each one of those areas, we will have the total work calculated, the total work being the work under the curve here. So it's pretty straightforward. So now, what is it doing in Excel? How do we calculate it, and what does it look like? By the way, there is a sheet, spreadsheet, which is provided for this lab, which has all the data, actual data coming from actual measurements done at the MSEL, our engine lab. So these are real data. So how do we deal with this? You see, we have several columns here: the crank angle, and the volume, the pressure, the work, the total work, total power, and friction. So you see how incredibly, how many pieces of information we get regarding the engine operation, just, starting with a little bit of data, which is crank angle basically, and pressure. We eventually get all that. So the second column here, if you remember, we get that from that equation here. Again, it's a one-time effort to enter it in Excel, and then it will do that automatically and easily. So that's the one you use. The pressure is provided, comes from actual measurement. And then you see here the work, the PV work, the PV cycle work, which is our area under the curve, the work under that curve. So that one comes from that expression here, which is related to the trapezoidal rule. So if you look at the way the cells are calculated, you've got the C7, C6 here. It's a pressure, so you add the pressure, divide by 2, and then you have the volume, the difference of the volume as another factor. So difference of the volume here is B7 minus B6, you see. So that's how, and then that's how you calculate all that, and then you simply, populate the rest of the data as you would do, transport that as you would do in Excel normally, and this entering data for each crank angle degree. Now the last part is the review of the thermal efficiency. Basically, well, it's about evaluating the work we are getting out of the machine over what it costs to get that work produced, and the work is what interests us. It's the work you have on a shaft, on the propeller eventually to propel a ship. In other words, the thermal efficiency here, eta, expresses the fraction of the heat that becomes useful work. And it is, I need to keep in mind that it is impossible for engines to achieve 100% efficiency. So that number is always under 1. And this is the reason for that. You know, according to the second law of thermal, it's impossible because some heat is always some heat is always wasted in an engine, always wasted. So that waste heat is actually what you see here. So it's this concludes the this presentation. So we'll see you in the lab, and have a great day. Thank you.